Welcome to the second lecture on iterative compression. In the first lecture, we set up the whole the framework, and we realized that all we need to solve to get an algorithm, we need to solve a disjoint compression of a problem. In this lecture, I am going to give you two problems. We are going to solve the disjoint compression problem in polynomial time. So, the two examples which will be constitute today's lecture is example of vertex cover, and then we will look at what is called feedback vertex set in tournament. Now, means this will be called FVST. Okay. So, first let us look at vertex cover. So, what is a disjoint compression problem for this? So, disjoint compression vertex cover, right. So, what is in the disjoint? Input is G, an integer k, a set S subset of Vg, mod S is less than equal to k, and G minus S is an independent set, right. Or in other word, sorry, k plus 1, S is a vertex cover. Okay. What is a parameter? Is k, and what is my question? Does there exist a set C such that G, first of all, G minus C is an independent set, second, cardinality of C is at most k, and third, C intersection S is empty. So, we are given a vertex cover of size at most k plus 1, okay, and we would like to have a vertex cover of size at most k whose intersection with S is an empty set. Okay. So, look at what is given to us. So, let us draw a picture to us. Here is an S, and here is G minus S, which is an independent set, and we need to find a set C here, right, such that C is a vertex cover and mod C is at most k. Now, notice what was the role of S? S is a vertex cover. So, every edge, hence every edge is like this. Every edge is adjacent to a vertex in S. Now, which implies that look at any edge here. So, this is a very simple thing, right. Look at any edge here, there are two ends points to it, one is x, other is y, right. So, what we know, for each edge x, y, okay, there are two cases. First of all, x belongs to S, y belongs to S. Second, x belongs to S, y belongs to G minus S. That is all that can happen. There could be an edge here. But imagine if this is the case, if this case occurs, but we are looking for a vertex cover C which is disjoint from S. So, if both x belongs to S and y belongs to S for an edge, then in this case you say there is no C that can be disjoint from S. So, now what we know? Such edges do not exist. So, only thing which we have is that for each edge, x is in the S and y is going across. Then for such edge, because x cannot be selected in the solution, you need to pick y. So, basically what is your C? C is nothing but n of S. That is it, right. So, in this case, if mod C is less than k, then return yes, else return no, right. So, that is it. So, we have solved the problem in polynomial time, which implies we have solved the problem in 1 to the power k times n to the power big O of 1, and hence by the whole methodology, this gives us an algorithm for vertex cover in time. What was that? 1 plus the running time of the compression algorithm. So, 1 plus 1 to the power k n to the power big O of 1. So, we get 2 power k n to the power big O of 1 algorithm for vertex cover, right. So, because we can solve our solve the compression version of vertex cover in polynomial time, the algorithm is very simple. Basically what you are saying that look, I gave you vertex cover, and we have also seen this idea already in our first lecture when we introduced the field of parameterized complexity, is that look, you are looking for a vertex cover which is disjoint from S, then better be that the graph induced on S does not contain an edge, because then there cannot be a vertex cover that is disjoint from S. Okay. And then you know that for every edge, one of the endpoints must be selected, and one endpoint is already part of S which you are not supposed to pick in. It means you have to pick up all the other endpoints into your prospective solution C. So, then you pick them up, right, check its size. If its size constraint is satisfied, you return yes, else you return no. And you can solve this problem in polynomial time, which is like 1 to the power k into the power big O of 1. I wrote this 1 to the power k just to illustrate that what will, if you fit into this the first lecture algorithm, the outline we made, it will lead to 1 plus 1 to the power k n to the power big O of 1 time algorithm for vertex cover. So, it was very simple. See, so once we set up the whole iterative compression setup, look at the kind of structure it already provided, that we can solve the problem in polynomial time by just following some simple set of strategies or methods. Okay. So, the second problem that we are going to consider is slightly more non-trivial, and so this is called feedback vertex set in tournaments. Okay. I will define each of these terms. So, what is an input? Input is a tournament and integer k. Okay. So, tournament, parameter is k, and the question is, does there exist a set f of size at most k such that T minus f has no directed cycle. Okay? Directed cycle. Okay? So, for example, this is a directed triangle. Okay? But look at this. This is, if you forget this direction, then this is an undirected triangle. But if I start from here, I cannot go back to the same vertex. So, it is not a directed triangle. Okay? And directed graphs that do not have directed cycles are called directed cyclic graphs. Okay? So, this is, or which you must have heard, DAGs. and there is a property of them. Okay, what is the basic property of them? If D is a DAG, okay, then D is a DAG, then there exists a topological ordering, okay, topological ordering of vertex set of D such that, so what is a topological ordering? So, there exists some ordering like V1, V2, V3 dot 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 Vn such that every arc Vi Vj we have that I is less than j. So, basically you can come up with an ordering so that every arc goes from a smaller index vertex to a larger index vertex. Okay? And in fact, what is known is that D is a DAG if and only if D has a topological ordering. Okay. And how is this topological ordering is fine is that you first find a vertex of okay, with what is called source. What is a source vertex? Source is a vertex which has only out arcs and no in arcs. Okay. So, these kind of arcs are not allowed. Okay. Then this is called source. Similarly, you define sink. What are sink? All those vertices which has only in neighbors, but no out arcs or no out neighbors. This is forbidden. This is forbidden. This is forbidden. Sink. Okay. So, source means, what is the meaning of source? Okay. No in neighbors. What is sink? No out neighbors. Right. So, look at the first vertex, like, so in the topological ordering, first vertex you can always show that it is a sink, sorry, it is a source, and if you delete this vertex, the next vertex will be form a source of the other guy, so on and so forth. So, the way to get a topological ordering is, you start with first V1 source of D, some V2 source of D minus V1, so on and so forth. So, every vertex is a source in the remaining vertex, which immediately implies that the only arc which is incident on them towards this is going after them, like all the arcs appears after V2. Okay? And so, this is why you can orient them. So, this is a very good property of a DAG which is used quite extensively in the algorithm, and you must have seen this, how to find topological ordering also using the algorithm which I told you, or using some doing DFS twice. Okay. But so one property, so now let us go back to the problem which we were dealing with, tournaments. So, what is tournaments? Tournaments is what is also called orientation of complete graph, or in other words, tournament has V1 to V2 n vertices, and for each Vi Vj I not equal to j, exactly one of Vi Vj is in arc set of T, or let us call it edge set of T, does not matter, otherwise just to avoid confusion. Okay. Edge set of T or arc set of T, or Vj Vi is in the edge set of T. Okay. So, what is the meaning of this? So, given a vertex Vi and Vj, either you have an arc edge like this, or edge arc like this. Okay, so at least you have arc in one of the directions. So this is why, what is the complete graph? A graph is called complete if for every pair of vertex there is an edge. So this is basically an orientation. So for each edge you have decided a direction to go from one vertex to other. So this is why this is a tournament is a complete set of vertices, and between every pair of vertex there is exactly one arc, either going from Vi to Vj or going from Vj to Vi. Okay. What is the property of, okay, notice that if T is a tournament, then if a T is a tournament and T is a tournament and T is a DAG, then it has a unique topological ordering, right? Why? Because the first vertex has to be the source vertex of T. It means this vertex, we know that starting from this vertex has arc to every one of them, right? And that arc direction is fixed because this guy has no one coming in, so every one only leaves him, right? So the first vertex has a property is that it's a unique vertex of out degree n minus 1. What is the property of V2? It is a unique vertex of out degree n minus 2, so on and so forth. And what will be the vertex Vn? Its out degree is 0. Okay. So there is a unique topological ordering. So there is like no more topological ordering. There is one fixed unique topological ordering of, right? So this is an important fact to remember. Okay. So we have taken a short break from our problem, and so I have told you a little bit about what feedback, like what about directed graphs are, what is directed acyclic graph, what is topological ordering, what are tournaments, what is a what is a unique topological ordering, or if T is a DAG, if tournament is a DAG, it is also called transitive tournament. Transitive tournaments. Okay. So now the one very special property which we will use for tournament is actually, and this is a key lemma for the first, what is the lemma? T has a directed cycle if and only if T has a directed triangle. Proof. Okay. This is a key lemma. Okay. This is a key lemma. What it tells us that if you wish to hit all directed cycles in a tournament, then it is sufficient to hit a directed triangle. And why it is this statement true? Let's prove this. This statement is true. Reverse direction is obvious, right? Reverse direction is obvious. Why? Obvious. Why? Triangle implies directed cycle. Okay. But let's look at a directed cycle in T, and it is not a triangle. Okay. Then I will show that it has a T has a directed triangle. Okay. So let C be the shortest cycle in shortest directed cycle in T, and we know C is greater than equal to 4, otherwise we are happy. So let's draw this. Let's look, it's a directed cycle. So let's and of length A, B, C, right? And there are more vertices here. Now, let's ask ourselves, okay, let's ask ourselves A and C, and this is an orientation of this cycle. This is C. Is right. So we know that either AC is present or CA is present. Okay. Let's ask ourselves what happens if CA is present. If CA is present, then in this case ABC is a triangle. Contradiction. That C is a shortest cycle. Okay. Which implies the orientation is okay. Now, let us look at now so CA is not present. Okay. Now, suppose AC is present, what happens? But now notice that we have got a cycle, this cycle C, we have got another cycle C prime such that cardinality of C prime is less than cardinality of C, right? Again contradiction, that C is a shortest cycle. So, we have been able to show, right? We have been able to show that what we have been able to show? We have been able to show the following lemma is that, right, T has a directed cycle if and only if T has a directed triangle. This lemma immediately gives us a simple branching algorithm, right? Simple branching algorithm, right? That you find a directed triangle A, B, C and recursively solve the problem on TFVS T minus A, K minus 1, right? If or so tournament feedback vertex set T comma K is equal to either this is true or TFVS T minus A, T minus B, K minus 1 is true or TFVS T minus C, K minus 1 is true, right? So, this will give you a 3 power K n to the power 1 okay, branching algorithm, right. What we are going to do is to design a goal to design 2 power K n to the power big O of 1 time algorithm for TFVS. Okay. And how we will do? We will see. We are going to solve. Okay. Let us not go up. Okay. So, what we are going to solve? We are going to solve disjoint compression tournament feedback vertex in poly time, and once we are able to do this, okay, we will solve, okay, we will write that, okay, okay. So, what is my input? It's some T an integer k and s, mod s is k plus 1, t minus s is DAG or transitive two-domain. K question: does there exist F subset of AG such that first mod F is at most K, second T minus F is a DAG or transitive tournament, is a DAG. Third, F intersection S is empty, right. So, same like vertex cover, we are looking for we are given a tournament feedback vertex set of size k plus 1 and we have some set of properties. So, the first thing as we did in vertex cover is that let us check, look. So, now what I am going to do, so we are going to design a polynomial time algorithm for, let us call it disjoint compression TFVS, okay. Disjoint compression tournament feedback vertex, okay. This is our goal. Okay. And how are we going to achieve this? So, first basic test. Okay. What is our basic test? And this is what? Is tournament induced on S a cyclic? Right? Because if there is, if tournament induced on S itself is not acyclic, it means there is a directed triangle or a directed cycle which is contained inside this, where all the vertices are forbidden to be part of F, then there is absolutely no hope to find a solution which will be disjoint from S. So, basic test, if no, return no. So, from now onwards we will assume that T of S, we assume from now onwards that T of S is a cyclic. Okay. Then what we know? Here is my S and here is my, say, T minus S. What do you know? That S is acyclic. It means it has a unique topological order. Let us fix that topological order. Okay. And I am going to write these vertices 1, 2, 3, dot k plus 1. Okay. I have named them. And T minus S, like unique topological order. Okay. Let us call this, I will call this ordering sigma S. Similarly, you have a unique topological ordering of T minus S. Okay. Let us try to understand what are let us call this sigma T minus S, this ordering and this ordering. Just notice one thing, that our goal is to take some vertices away such that S union T minus S, or rather T minus F is a DAG. Okay. Now, let us look at an ordering sigma of T minus F. Okay. Now I claim to you that look, if you look at this sigma and look at the sigma restricted to vertices of S, then this is exactly equal to S. If you look at sigma restricted to T minus F minus S, this is exactly equal to sigma of T minus S. So basically what happens is that the vertices which are going to remain from this ordering, right, and the vertices which are going to from here. So if you look at the topological ordering of these vertices after deleting the solution vertices, then that's also a tournament. So that also is a unique topological ordering, and in fact the great property of that topological ordering is that maintains the topological ordering already given on S and on T minus S. Okay, that's a property. Okay, so now some reduction rule. Okay, what happens? So now what we know about this? All the arcs are going like this here. Okay, now let's fix a vertex. Okay, let's fix a vertex such that I have, let's fix a vertex such that it has an arc like, it has a then what does it imply? Suppose it is some vertex 2i. So if basically this is rule is, what is the reduction rule? Rule is, if there is a triangle with two vertices in S, then select the unique vertex not in S in F and decrease k by 1, right, which is same as, so let's apply now, apply rule, let's say 1 exhaustively. So we have applied this rule exhaustively, right. So what will happen? So when you apply this reduction rule exhaustively, either k have become 0 and there is still triangle, then you can say no, or you have applied this rule 1 exhaustively and now you have graph where you cannot apply this reduction rule and there is some value of k. Now let's try to understand how does that world look like. Okay, this is an important. Okay, now let's fix a vertex. Okay, now let's fix this vertex and let's ask, how is the orientation of arc 1x? So notice the orientation of arc, or let's call this vertex x. Okay, if it is going from 1 to x, or it could be going from x to 1. Okay. Okay. So suppose it went from 1 to x, then I claim to you that look at 2, right? Look at 2. What is an arc? Suppose it goes from x to 2. Then I claim to you that you cannot have any other vertex from 3 to k plus 1, okay? 3 to k plus 1 such that you have an arc of this nature. This cannot happen because otherwise x, 2 and I and x will form a triangle. So what happens is that you have in arcs coming in, and after that once you have out arc coming going out of x, you cannot have any other in arc coming in. So this, like you could have in and then out, 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 out. But you cannot have in, out, in. This is not going to happen. Okay? You cannot have out, 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 and then in. This is it. So when you, the moment you get out, like the first vertex you get x to some vertex which is out, then to every other vertex you will get out only, otherwise reduction rule 1 would have applied. Okay? So basically what happens is that after this is that you could have like this, you could have like this, but then once you start to have this, then to everybody else you will have this. Okay? So this is, and this is a property which holds for every vertex. Like there is only one change from in to out, but there is no change from out to in for a particular vertex. Now what does that means? Look at this. So if a vertex x is not part of F, then where this vertex x will? Then if I look at sigma, then my vertex x is going to occur after 3, right? And it has to occur, so suppose this is 4, that it starts to go out like this. So so suppose this is a vertex, so where x is going into the location between 3 and 4, because then only all the arcs from 1, because you know that 1, 2, 3k is going to be the order in which they are, because they are not going to be deleted, only then this and this will have arcs like this. So either x is part of my tournament feedback vertex set, or x is going to be in the location 3 to 4, right? So for notice that for every vertex there is a one particular location where it can belong to. So I am going to write for this particular vertex location, let's write it with brown, location 3. So similarly there could be, so a vertex could come here. Why? Because every vertex goes in, or a vertex could come here. Okay? So I am going to call a vertex which can come here location 0, a vertex which can come here location 1, so on and so forth. So I could have 0, 1, 2, so on and so forth. Okay? Now let's look at sigma t minus s. Look at, okay, so this is a location. Let's ask ourselves, this is a vertices which will go into the location. Now let's ask ourselves that what happens if I have two vertex, okay, okay, I have two vertex, let's, okay, let's ask ourselves what happens if I have two vertex. He says I need to go to location 5, and this vertex says, well, I need to go to location, okay, or say this vertex says I need to go to location 3, and this vertex says that I need to go to a location 1. What is the meaning of that? The meaning is that 1 has, what is the property? That x says that I have to go to location 3, meaning x, this particular vertex has an arc of the following nature. Up to this, let's say, let's draw, yeah, of this nature. And what does this say? Look, I need to go to location 1. It means he has arc, maybe let's not just draw orange, right? And after that he has an arc of this nature. He has an arc of this nature. Okay. But we also know that we have an arc from 3 to 1. So let's just try to see what happens. Now I can go 3 to 1, okay. Then I can go, right, I can go 1 to 2, right? And from 2 to 3, I can come back. So if there are two vertices in this ordering such that that a vertex which has a vertex has a higher number and a vertex which has a lower number, if they are in a different this thing, then they will form a triangle. So what does it mean? It means if we look at the vertices of T minus S union F and look at the ordering of these vertices, look at the numbers of these vertices, right? They must be in non-decreasing order, because if they are not in non-decreasing order, then it will form a cycle. So what is this problem? Then our problem is nothing but, so what we know, and if you give me any non-decreasing order sequence here, like if you look at this sigma s minus 1, if you give me any sequence which is non-decreasing, I can fit this into this without getting a triangle, because look at all this non-decreasing number, like put them where their location, because then what happens? Then everyone goes to their location and every R goes from left to right, left to right. So notice that if I delete a subset of vertices, which is my tournament feedback vertex set, what I get is a sequence of numbers which are in non-decreasing order. And if you give me any non-decreasing sequence, and then complement forms a tournament feedback vertex set. So what is this problem? So the problem we get is, what is the problem we get? Delete from vertex set of T minus S to make number sequence non-decreasing, right? So what did we say? Look, if from this number sequence, if two numbers survived such that one has higher number, like higher number appears before lower number, then we get a triangle. This cannot happen. So it is always the case that my number sequence is monotonically, like number sequence is non-decreasing, right? And if you give me any non-decreasing sequence, then I can fit this and get a tournament. So basically my problem has become, we get is delete from Vt minus S to make number sequence non-decreasing. But what is this problem? This is a very famous problem which you have done in your class. This is nothing but longest non-decreasing sequence, right? And this can be done in order n square time, I think, using classical dynamic programming. Okay. So let's just go back and recap what we did. Okay. So we had to solve this disjoint compression problem. Okay. So first we made sure that tournament induced on S did not form a cycle. Then we said, okay, fine, it has a unique topological ordering. Then we put this. We found the unique topological ordering of T minus S. And our main observation was that after we delete vertices, we basically are merging these two, we are merging sigma S and sigma T minus S in a way such that their relative orderings are preserved and every R goes from left to right. This is what we observed from here, that if we look at the combined, after deleting F, if we look at the combined topological ordering, then if I restrict myself to S, the topological ordering is preserved. If I restrict myself to T minus F minus S, it is preserved. Okay. And then we first applied one simple reduction rule that, look, if there exists a cycle that contains two vertices from S, right? If there exists a cycle that contains two vertices from here, then I know if there is a triangle that contains two vertices from S, then there are only 3 vertices and 2 you are forbidden to be picked into your solution, then you have to pick the last one. So, this is what this reduction rule implied. After we apply this reduction rule exhaustively, we get into a problem with the following property. So, what we did? Okay, I said look at a vertex X. If you are either you are deleted, if you are not deleted, what is the place that you can you have, what is the location with respect to sigma S that you can belong to? So, we said that look, the great property happened after reduction rule 1, that for any vertex, like if I start the follow from 1 to k plus 1, then there is exactly one place, unique place where it shifts from being in neighbors to out neighbors, and this series continues, right. So, it could be that X, everything X is just out neighbor to, then what is the location he can belong to? Then this guy can belong to the only place which is 0, because X cannot be placed anywhere else without violating the topological ordering constraint given by sigma S, right. So, there is a unique place where X could belong to, and notice that and I write 0, 1, 2, 3 based on which location can you belong to. Now, notice one thing, because even here they have to maintain the constraint. So, notice that if all these numbers 0, 0, 1, 2, 3, all if this was an increasing sequence, then if you would have placed these vertices in the order in which they appear in sigma t minus s in these locations, then together they form a sequence where every arc goes from left to right. Okay. But this may not be true, right. But we notice that, hey, look, if we delete the tournament feedback vertex set, indeed these numbers must be in increasing sequence. Why? Because if they are not in increasing sequence, then we actually get into we can form a triangle. Okay, great. So, basically we have reduced our problem to find a number sequence as large as possible, or to find a number sequence that contains all the vertices of t minus s but k of them. Okay? And that problem is nothing but a longest non-decreasing sequence of numbers, and that we can do it in order n square time using classical dynamic programming, or maybe n cube for sure. I think n square is possible. Okay, so that should be all for 2 lectures for this. So, you notice that, right, the disjointness constraint actually gives us so much structure that several times we can actually solve the problem in poly time. For vertex cover, it was pretty easy actually. So, vertex cover was even more easier, because all we did for vertex cover is that, hey, all we did is the graph induced an S independent, if not, say no, otherwise take all the neighbors outside. Okay? And then for tournament feedback vertex set, we reduced the problem to finding longest non-decreasing numbers. Okay? Okay? So, towards that, we first defined what is the notion of directed graphs, what is the notion of DAG, what is the notion of topological ordering, and we also proved this very nice property in tournament, that tournament has a directed cycle if and only if it has a directed triangle, and we utilize this property to constrain ourselves to look at only directed triangle and not worry about any directed cycle, because the moment we are able to hit all directed cycles or obstruct all directed triangles, we are able to hit or obstruct all directed cycles. Okay? And that immediately gave us 3 power k simple branching algorithm, but using iterative compression, we are able to design for disjoint version a polytime algorithm, which immediately implies that 2 power, which immediately implies two power k n to the power big of 1 time FPT algorithm. Okay. Some remark, not very important, but it is an important remark. There is an algorithm faster than 2 power k 1, I think, 1.61 to 8 to the power k, which was obtained using some very nice clever trick. And for approximation, a simple approximation algorithm for this problem is that you take the triangles and delete it, find another triangles, delete it, and that gives you a factor 3 approximation. And it was, but it is also can prove that you cannot have under some complexity theory assumptions, such as unique game conjecture, that you cannot have 2 minus epsilon approx algorithm. And only recently in 2020, randomized factor 2 approximation was given. Okay. Obtaining a deterministic factor 2 approximation for the problem is still open. Okay, and the algorithm is, this factor 2 approximation is quite interesting and simple, and it is like just divide and conquer or merge sort. So if someone is interested, can write to me and I can give you a pointer to this. But these are just a small set of remarks that has nothing to do with the lecture, but just to give you a fulfillment of what's known about these problems. Okay, with this let's conclude this lecture, and we will continue our foray into iterative compression a little bit more in 2 more lectures. Okay, see you then. Bye bye.